Hello everyone, I want to welcome you all and I want to talk about violence against children. It is a big no-no. Get out! Get out! Get out! Hello everyone, welcome. Today I'm going to continue this series about, logic circuitry and Circuit Maker 2, a Roblox experience made by iSmall Beef. I still did not check the number after his name, but we're in Circuit Maker 2 right now. So today what we're going to talk about uh, is the truth table, which is very helpful for planning out your circuit truth table circus, and then binary. It's I'm going to talk about how you would count and how math would work in logic circuitry because, well, we don't have numbers, we only have 1 and 0, so how would it work? But before all of that, I'm going to talk about a few things I missed on the first episode. So some of you may have noticed that I didn't show the total of 8 gates, but here there are. I didn't talk about it because I wanted to shorten it, but I already told that there were knotted versions of the AND gate, the OR gate, and the XOR gate. So a buffer would act like a single inputted OR gate, and the NOT gate, I already showed you guys this. But yeah, those are the 8 gates in Circuit Maker 2. But there's 6 gates here, and then the buffer and the NOT gate are not showed in Circuit Maker 2 in logic notation because this also acts as a buffer, this also acts as a NOT. But this is how they would look. The buffer gate would just be a triangle, and the NOT gate would just be a triangle with a little circle. There's chaos in the background. Anyway, so truth tables. A truth table is a table of data including the possible inputs of a circuit and the corresponding outputs of the circuit. Very helpful for planning out your circuit, but it's a bit tedious to make. You can get a website to do it for you if your project is big. So here's just an example truth table. I'm using the OR gate because I'm using the OR gate as a 1 because it's green, and I'm using the NOR gate or NOT gate as a 0 because it's red. And it's just very simple. I can make truth tables in Circuit Maker 2. Alright, so in this particular circuit, if A is on and B is off, which A and B are the inputs, the output will be off. If both are off, A and B, then the output will turn on. But if both are on, the output will turn off. So this is just an example of how these tables will work. You can make one in like a notebook or something by just aligning the inputs and their corresponding output. You can use this to plan your circuits. Here's some truth tables right now, not only as examples, but to help us understand these gates here. So this is the buffer. I think it's pretty obvious. If the input is on, which is here on the left, then the output will be on. If not, the output will be off. Here's the NOT gate. If the input is on, the output will be off. But if the input is off, the output is on. Look, it's green here and it's lighting up here. Now, quickly over to the OR gate. This has two inputs, so we're using two inputs here, two inputs here, two inputs here. You may have noticed there's three possible inputs that are shown here, but there's another one if A was on and B is off. But it's the same thing because we talked about this. The OR gate turns on if at least one of these inputs are on, so it doesn't really matter. Anyway, let's start. If both inputs are off, then the output will be off, which you can see here. Both are not lighting up, so this will not light up. This is the OR gate, by the way. If at least one of these inputs are on, it will turn on, and we can test for that by turning on one of these inputs. Oh no, the server's broken. To test for that, we can turn one of these on. Oh look, one of them's already on, so when at least one is on, it's on. Finally, if both inputs are on, the output will be 1. Turn both of them and it's still on. Now for the NOR gate, which is this, if both inputs are off, the output will be on. As you can see, both inputs are off, the output is on. If at least one input is on, then the output will be off. So we turn one of these, it's off. And if we turn both of them on, the output would still be off, like here. Now let's continue to the AND gate. If both inputs are off, the output will be off. Let's turn both of them off, the output's off. If at least one of these are on, the output is still off. When both are on, it's on. So you can get the you get the gist of this. We can reconstruct this truth table like so. You can make this anywhere. You can use ones and zeros, the words on or off. You can use anything that represents off or on. So this would be still the AND gate's truth table, missing one possible inputs set. But yeah, and then this would be the truth table for the NAND gate. You can pause to check it out. This would be the truth table for the XOR gate, which is the purple gate. And this is the XNOR gate, which I did not talk about, but that's a knotted version of XOR. And then I'm going to talk about binary. Now binary is also about numbers, ones and zeros. Binary is a counting system consisting of 2 digits. It's a bit convenient. It's quite convenient for logic circuitry because you can assign the numbers 1 and 0 to on and off. Now to make this simpler for us, let's talk about decimal. Now decimal, I'm not talking about the point. I'm not talking about the decimal point like in 3.4. I'm not talking about that. That's the name for our counting system. Now decimal has 10 digits from 0 to 9. So these are the possible digits that are in decimal. Now to make bigger numbers than 9, we just combine these digits. So let's try viewing the decimal number 427. So how it would work is like this. We start from the very right here on 7. The first place would be 1's place. So to calculate the value of this, we go 7, which is our digit here, times 1 because it's on the 1's place. And then we add that to the rest of the numbers, but we gotta calculate their value first. We go on to the next number, which is 2. 2 is on the 10th place instead of the 1's place. So these are powers of 10. So 2 times 10, there you go. Finally, we have 4 on the 100th place, still a power of 10. This time it's 10 to the power of 2. So 4 times 100, and if we add these up, we get 427. So that's how we would count. In binary, we only have 2 digits, 0 and 1. So let's try looking at the number 10011. So from the start, from the very right, we have 1's place. There's a 1 there, so 1 times 1, add that to the rest. The next place is the 2's place this time. It's not a place of 10. It's not of a power of 10. It's of a power of 2. 2 to the power of 1. Anyway, 1 times 2, add that to the rest. And on the 4th place, this time we have 0. Which means that's just 0 times 4, very easy. Same thing on the 8th place, which is the 4th place, 8th place. Then finally we have a 1 on 16. So if we add these up, we get 1 here, 1 times 1. 1 times 2 would become 2. And these become 0, so we don't consider them. And then there's 1 times 16. 1 plus 2 plus 16 is 19 in decimal. So the binary number 10011 is equal to the decimal number 19. This would be how to do math, and there are circuits that turn binary to decimal, or even hexadecimal, which is 16 digits. These are the digits. The last digits are the letters A, B, C, D, E, and F. Those are the last 6, and then the rest are just decimal digits. Now you can try figuring this number to A65E, this hexadecimal number to A65E yourself. You can try figuring it out. You can try turning it into decimal, but you don't have to. Now these places are on powers of 16, so you know it's a huge number. You can make other hexadecimal, smaller hexadecimal numbers for yourself, then you can try figuring them out. But they're for the future. So that is a wrap up for this video. I talked about the truth table, how it works, and how you can use it to plan your circuits. And then I talked about our counting system and logic circuitry, which is binary, because we can't have decimal, we don't have numbers, we only have on and off. And yeah, thank you for watching. If you made it this far, I want to make it rewarding for you. So I'm just gonna say, hopefully this knowledge helps you in your logic circuitry journey. hope you have a good day. Goodbye.